Reaching semilinear sets and automata with one counter. This is about joint work with Yousef, Shakiba and Georg Zetzsche, Yousef being a student of Georg's. I'm going to be talking about one counter automata of sorts. I should definitely caveat. I've never given a short 90-minute seminar. I've prepared a lot. I think I've prepared too much. So if I go too fast, too slow, too long, just shout at me, please. Okay. So I'll start with the definition of a model. Good point. We have a finite automaton with a counter. So I don't know, from a state P to a state Q, I can have some updates. So from a configuration P with counter 5, I can reach Q with counter -7. So to be precise, I'm working in integer semantics. So the transitions are integer and the configurations are also integer. I will touch on later, but not focus on natural semantics, where all the transitions are natural numbers and all the configurations are natural numbers. And I'll also touch on the missing semantics when the updates, the transitions can be integer, but the counters must remain non-negative. That's semantics. So I'll be focusing here. I'll come back to those other two later. Right. And the most basic question comes from two problems that I hope everyone's heard. The first is reachability, which is in a machine from some initial configuration, can I reach some target configuration? And theorem is that reachability in integer one VASS, which is this setting, is NP complete when you're assuming binary encoding. So that's going to be the assumption for the remainder of the seminar. I won't bother showing you why you can do a subset sum reduction. It's not too difficult. And then there's coverability. Very similar problem, but instead from the initial configuration, I want to be able to reach a configuration that's got a counter value that is at least target. And coverability is much easier. In fact, it's in a C1, but the point is that it's easy. It's 100 times solvable. To see it's 100 times solvable, you either have a short path, or if you don't have a short path, you'll see a cycle. And negative cycles aren't going to help you reach your target. So you only see positive cycles. If you see a positive cycle, you can take it. You can take it as many times as you like, get a counter value that's arbitrarily large, and then without even thinking, go to the target. So this is in P, it's not hard to see. This is anything hard. I haven't shown you. But the question that I care about is not necessarily reachability and coverability. It's kind of why is coverability easy and why is reachability hard? Like, is there something more to it? Can I ask a more general question?
For the remaining two semantics, it's the same, right? Continuous P and
yes. So you can ask the same question.
Why is semantics?
We studied all of them. I just chose to present this on because it has the most interesting theory, in my opinion. These two end up having, for the remainder, very similar. You can just imagine talking about natural numbers and it won't change much. But for traditional one VASS, things are quite different. But the same question applies. Like, why is reach hard? Why is covered easy? And so, what are the contributions? So if you listen to this and then fall asleep, this will be a success for the seminar. Is the problem that we studied. It's fairly technical. Try to do this slowly. I don't like being paused. So some sort of generalized reachability problem. So I'll call it reach. And I'm going to just throw the semantics in there so you can have an error of us in there. S. So fixed is a semilinear set. So it's a P plus one dimensional semilinear set. It's basically parameterized by P, many integers. I will explain what's going on in a minute. This kind of looks confusing. And I will give some examples. This will be cleared up. So I define one problem for every semilinear set. So I'm really giving you a family of problems. And the input to the problem will be one-dimensional machine. So one ZVAS, for example, or Parikh or normal one VASS. An initial configuration is
It's resource semantics is one of the best developments, right?
And a parameter vector or an instantiation of the parameter vector. And the question is, in the VASS, can I reach the target state with a counter value such that it satisfies the conditions required by the semilinear set? Examples are going to help this. And I will try and put them on a board and then commit them to a board because I'll point examples frequently. I will give you 6 examples so that there's nothing left to not understand. So the first, I can represent reachability. If I give you the set S, this is just reachability. I can input whatever one VASS I want and then initial configuration, and I give you a value T that I want you to reach. Right? That's fairly clear cut. 2 is coverability. I can give you this set. Pretty obvious.
The other way around.
Thank you. Yeah.
And P is one in both places, right?
In this case, P is 1, P is 1. I will give you an example of P is 0 and P is 2. But I won't focus on them too much. 3 is 2 parameters. So this is like covering and avoiding. I want to reach a value that is at least T1 and not equal to T2. For example, or I could have, so this is a set with no parameters, so just be integers such that X is odd, or X is 0. That's fine. This is all present over final. I could have single parameter, so Tx such that X belongs to an integer. Bit suspicious. And I can also generalize, not generalize, I can change this slightly. And this last example is the one we'll focus on. And I'll explain why it's interesting in a moment. Which is you either reach an interval or you reach a negative number. So I generalize reachability and coverability, and I've got loads of problems. And I will show you in a moment, but I'll give you a simple test, a dichotomy that you can apply to S to work out whether your problem is going to be easy or whether it's going to be hard. So I'm bucketing all the coverability-like problems together and all the reachability-like problems together. So to do that, I need to give you more definitions.
Could you maybe, why not, this input, you're doing the just the set, the senior set? Not the reason.
So yeah, this is, I'd have to talk about natural. So if I just give you, I don't know.
It's like you want the problem to have some parameter,
Yeah.
so that you can study the computational complexity as a function of the parameter.
So
You can study complexity as a function of a senior set.
you could, yeah, that's a reasonable question. We could do that.
We fix. All right, they're going to fix. So then it's kind of the fixed target. That doesn't sound good. Fixed target.
So
I see.
But integer VASS, it's a reasonable question, but for if I have natural semantics, all the updates and are negative, this target set has like in fact, any finite set, so I can just have any finite set here. This will have easy reachability. So I just look at the graph, look at the transitions that have zero effect and see reachability. But then if I give you just single parameter, then reachability is hard because I can now encode subsets out. I can set the target value to whatever I like. So it makes an obvious difference with the semantics, and it does make a difference.
Yeah, you want to have families of sets. That's what you do with them.
And yeah, anything with a parameter here should be fine, for example. Okay. I will now look at
Is this the first instance of a situation where you have a family of computational problems which are parameterized by a semilinear set, and then you study the complexity as a function of properties of that semilinear set?
I haven't seen it before, so probably. I mean, maybe some logicians who studied similar problems, I don't know. But for automata, or specifically counter automata, I've not seen this. So I'm sharing this because I think it's interesting on its own. Yes, and I can, without thinking, now identify problems that are easy. So when I say hard, I mean NP-hard. When I say easy, I mean in AC1. And I'll go through why in a moment, but I do need to give some more definitions. This one may easily, and the reason I gave these three at the bottom is to show that although they look similar, the last two, their reachability problem is hardly easy. It's kind of unclear why at this stage. So for that, I need to define the measure in which technically a semilinear set is hard to reach, but it's easy to reach. So I will now define some density measure. So I'll go through this. It's going to be technical. Stop me if you're confused. There will be pictures with some of the examples. So let A be semilinear. I'm going to define D of Ln to be the inferior over the matrix of how does A intersect with an interval of size 2n plus 1 centered. So to give a picture, this is our example 6. So when I've got like built-in line that's in the set, and I've got a dashed line not in the set. So it's 0 to minus infinity union t through 2t. I can stare at the density of this set. So if I have a point here, and I look at the interval surrounding x, right? So if I look at the interval x minus n all the way to x plus n, then I know that I'll have at least half of the points on the left-hand side, and this interval can grow and grow and grow, and I'm going to continuously get the left-hand side. And on the right-hand side, I'm maybe not going to have points, maybe have some, but I know that the density around X is the least. And now I can look at, is that other colors of chalk?
You have to prepare that in advance.
No problem. Just one color.
It's exactly 1/2, right? Because if you have very big intervals.
So at this point here, the density is actually a quarter. So if I look at the interval here, sure, the density is a half. But as I grow up all the way out here,
But in the limit,
But in the limit, right? Because for very big
depends on the value of t. So you're jumping ahead a little bit. So if t is very large, it depends on t. But yeah, I agree that for this, if you have a 15,
can it
yes,
depend on t?
yes.
But doesn't this finite interval get annihilated in the limit? Like if your window is huge, then this finite interval plays no role. My intuition is that 50% regardless of choice of x.
You're taking in the leaving in. I'll go ahead and then we'll ask it again. There is also something I'm hiding here that I'll come back to in a moment, which is we catch modulo classes. So, but we'll come to the K in a bit. There's then the density of A is the inf over each modulo over points in A of density, the local density of X.
It's called supremum over K.
This is inf. So inf over K, inf over X, density at that point. And then I'll go further if I let S be a semilinear set with p parameters, then the density of S is inf over all parameter vectors of the density of the offsets given by a parameter. So X along with Z, which is that. That's where I think the force comes from.
Just in your example, if we take x on the right of t, then this is on the right of that. So the empty space.
Okay.
Then the zero or x a.
So I only look at local density of points in the set.
Okay.
So precisely the density here could be as low as you have this quarter, so you get t, that's 1 points over, and then the width down to 1, so that'd be 2 lots of 2 to the minus 1 minus 1, which is roughly a quarter of the large t. Any questions? If this doesn't make sense, like, please
I just
skip the cake. Go to the
I don't understand I don't understand the K.
Okay, I'll come to that with an example.
The case on the over, it's in the nominator, not in the denominator. Okay.
Yeah, the K, yes, because I'm only looking at, so this set is not the interval centered at X with width 2k n plus 1. I only take every k point.
So this is the smallest density of A in an interval whose finite interval whose center is an A, yes?
Who centers in it? Yes. I will now touch on example 4 for this modulo. Look, so yeah, look at the set. S where you're either odd or equal to 0. It's quite hard to draw. So I have 0 here, and then you'll get all the odd numbers. So 1, 3, 5. It's 1, 3. It's 5. If I look at density with k equals 2, for this set, centered at 0, then the density will be 0, because if I look at an interval that hits every other point, so hits 2, hits 4, hits 6, and -2 and -1 and -6, I will only have 1 and 2 n plus 1 endpoints. But then if I look at density at any odd number, for example, so if I start here and I look at points that are 2 apart in an interval, then I'll hit everything, so the density will be 1. Does that make sense? Does that help? That's the only reason, and I'm going to be sweeping this right under the carpet because it makes life uncomfortable. But we sweep it formally under the carpet, I hope. Any more questions? Is that okay so far? I'll give the main theorem and then I'll come back and we'll study this one a bit more closely. Next. The semilinear. Very hard, like possible. It's easy when it's dense, it's hard when it's hot. And so now I can just stare at these sets and I can write down easy, hard, easy, hard. The singleton, for example 1, is obviously not dense. I can only pick the point x equals t, and I look at the intervals that span either side of it. There's nothing else in the set, so the density will be 0 for coverability. Density will be a half for the reason that we saw here. There'll be a value t, have everything to infinity, nothing down to minus infinity. The density here will then be a half. So probably easy. And you can do the same here. If you have a hole in your coverability set, density doesn't drop, so it will stay easy. Example 4 was hard because we found a modulo for which density was 0. And so you can imagine just taking an instance of subset sum, doubling all of the item values so they're all even, and now trying to reach a target will be hard. 5 and 6 I've not separated yet. I'll now look at a simpler version of 6. It kind of like has a nice feeling that I'll try to get to later.
And I have a question about the semilinear sets.
Yeah.
So the class of semilinear sets of positive density, does it have nice closure properties? It looks like should be quite robust.
On the union, yeah, if you're positive, if you have 2 sets that are dense, the union will be dense. Intersection though.
Duration, this is natural.
I don't know.
I will get equivalent. Yeah.
Yeah, I've not studied that. All I know, and this is gonna be the final thing, testing this is kind of like the meta question on top. If I give you a semilinear set, is its density greater than 0? That's decided.
Density is always a rational number.
Yes, I think so. We are very lazy. We turn it into something which is perfectly definable. You're kind of done.
The density is definable.
Yes. I'll get to that, but I won't prove it. It's too much. Yeah, so there's a half answer for you. Okay, so I'm going to stare at 6 in a bit more detail. I'm going to simplify first. So kind of a nice toy problem I think has some nice properties inside. So consider the following instance of subset sum. This kind of negative or interval. So the input will be your items, x1, x, and t, which will resemble the target. And the question is, does there exist a collection of items such that their sum is either negative or non-positive or in the interval. So this is kind of like some very restricted version where I've removed the information in the state space. This is polynomial time sample, and it's not hard to see why, and I think the idea is nice. So first, stare at the items. If there's a negative one, you win. So if you see rather not positive, then you can just have the set that satisfies the target and just factor. Similarly, if you see one where the item just overloads the interval, then you'll also have it. So now you can assume that all the items either have values between 1 and t minus 1, or they're strictly greater than 2 and t. Well, now if they're between 0 and t minus 1, or rather between 1 and t minus 1, or strictly greater than 2t, then an item of strictly greater than 2t is not useful because you can't reduce your sum total. So now phrase that. And now all you need to check is the sum of the remaining items is greater than t or greater than the root of t. So if now the sum of well, all I then you're happy. Here's a picture, and it kind of just start marking the partial sums x1, then x1 plus x2. And notice that because you know that you've binned off all items of value greater than 2t, you don't have any negative ones and you have nothing inside of the interval t to t. You've only got items that have got values 1 through t minus 1. Then the next sum can't jump over the fence all the way over to t2, so you must land inside here. And you're guaranteed. So in a sense, as long as you have a total sum that's enough and the set of reachable values is somehow dense, and this window is wide enough relative to the item values you're given, like reachability, or rather the subset sum problem is easy. This will remain this kind of feeling. Okay, so I'll now sweep some stuff under the carpet that doesn't look easy.
Is it important here for the upper bound that the whole S thing is Semilinear? Would it be generalizable to the case when only for every parameters, for a couple parameters, you get a Semilinear set?
I don't think I understand.
Imagine that the dependence on parameter is not linear, it's like quadratic, like t squared to t squared plus t. Right.
T squared to t squared plus t will be easy, but if I gave you
T squared to from t squared to 2t, whatever.
that might be okay, but something like root t to t, no, really don't know.
Do you really use the fact that the S, the whole S is Semilinear?
Yes,
Yes.
we really use that. And it's kind of an arbitrary choice, actually. You could have argued, oh, why did you need parameters? You were kind of getting at that. You could have maybe restricted to semilinear sets with just one parameter. That's also a reasonable restriction. We basically set the bar high enough where we could do work. So because you could also just have any set more general than semilinear. Don't have an answer for you. This is just our choice. I think that some of our ideas might be usable, but some of the preliminaries that I've just about to talk about will just get destroyed instantly.
I guess it would be in swap, so I understand, sorry for saying that the S would be defined with polynomial.
Whatever could
But I guess it would be hard to avoid Hilbert's 10. Because probably your polynomial can never give you a 0, that can be.
No, I mean, S is fixed, right? So you can have nothing that produces. I mean, is it
Yeah.
enough to know that output Semilinear set?
That doesn't help you too much because you can have like a fixed polynomial which represents a universal Turing machine. So my intuition would be that using S.
No, the question was, is it using the proof that the S full S is similar, or is it only use the whatever parameters? With the similar set, which is the case.
That's a good question. I'm not sure. We certainly use the latter for all. So there's the restriction.
Is it like the whole thing? Will you need it to be similar in the proof? No, it's ACG. If you want.
Good
I would
question.
guess, Parikh, that you should be able to cook up a situation where you have an S, which always produces a semilinear set for every choice of parameters, but nevertheless encodes Hilbert's tenth problem. Like this, I think it should happen. It's just an intuition, huh?
I'll talk about it over K, because I can stare at exactly where we have the dependence on the global S rather than the individual S T's. Okay. Anything else?
Yes, so these examples 1 to 6. Do they cover cases from the literature which were already known to be NP complete or AC1?
When you say literature, you mean individual questions
Yeah.
that are already studied.
That's right.
Not much more than you could. So 1 and 2 obviously studied. 3 has been studied, but not exactly. And it was also shown to be easy, not AC1, but they studied a more general version of this that we cannot capture. So it's close by. It's a reasonable question. I don't think, this is not in literature, right? This is just the first hard example that I was given. It's the kind of question you can give to someone undergraduate in an exam, right? So in that sense, it's in the literature, but not in, because I don't think it's supposed to be shown in AC1. The AC1 specific part is not super interesting because this is already known. We also get an AC1 NP dichotomy of the other semantics. And that's most interesting in VASS because coverability was not known to be an AC1 beforehand. So we have to do some improvements to just coverability to start with to even get half dichotomy. So yeah, I hope that half answers the question. Okay. Anything else? Well, unfortunate preliminaries have to be stuck on the cap. So I want to keep that. Do you want the problem statement still on the board? Probably can go, right? First preliminary. We can just reduce to the A-type fair case. This is not obvious. I'll just write it down and pretty much leave it there. I'll give you one of the ideas we use inside because it's so for a semilinear set, the problem where the only difference between reach and AC reach is that the import also must be acyclic. It's the only difference between these two problems. The main idea in sums is to use Eisenbrand and Schmol's ILP integer code of the door style.
So what's AC? What's on the right? This is
AC reach. It's the same problem as the reachability problem. So you have the set S is fixed. You have an input automaton, input target, input parameter vector T, and an initial configuration. But the difference between this and that is the input automaton must be acyclic.
okay.
That's it. It's a large step.
And cycling any path is actually of length size of automata.
This is surprising.
When this in particular solves reachability in NP, right? Correct.
No,
If you have that fact,
Uh-huh.
you easily have reachability is in NP. Okay, but this is not.
We look at
but
hardness.
That's not a vast amount.
Yeah, well, I mean, reachability in acyclic machines is still hard.
Just to be sure, acyclic based on the states.
Yeah, just on the structure here.
And this is for the single, only the one thing, right?
Yeah, so this Z is just for this. This also works for N. Does work. Well, I actually think it does, but we don't write about it. That's a separate thing. That's okay.
It would be challenging.
What is comment sex about the VASS not? Surprised maybe it was for
Just one challenge.
I think it's possible. Maybe not for all that. Yeah,
Nie no, w sensie nie.
but yeah,
Polityczne, ale dodatkowo.
but yeah, specifically of interest about it. What about that? Super clear.
Byłby jeden was. To nie jest to.
Any more questions? Okay, Carol, Rory, like results. In short, you can argue there's an exponential bound. That means you use cycles at most exponentially. And so then you can, in a sense, unroll the cycle, not into exponentially many copies, but into one copy where you have 1 times the weight, into one copy with 2 times the weight, and one copy with 4 times the weight. Chain them all together. Now you can choose any exponential number of times to take that cycle. Morally, that's the very long short of it. And the other preliminary is that we're going to remove the modular constraint. So you don't have to have a headache, and I don't have to have a headache.
This that works for one-dimensional or for one-dimensional
No.
space,
Um,
works for general.
yeah, I just didn't talk about it, but yes, it does. This is, yeah, it's pretty cool. Because they're results in general. That's the reason I asked.
So what kind of reduction, it's block space, p time? It's written there, sorry.
Yes, I also didn't highlight it. Okay. We just blow up the machine, but polymer. But the reason it works is useful. Any other? Okay. And then brilliant 2, what's going to shut us on the graph now. These will pop up later. I'm telling you them for a reason. I would not talk about them. We can remove. I've got a fairly long length statement that's quite nice, but I think for the sake of time, I won't focus on this. I don't think it's super interesting. Basically, I'm just going to strike off example 4 from the board and say it's illegal from now on. Very roughly, if there is a modulo class that has 0 density, then the problem will be hard. Otherwise, if all modulo classes are easy, then we can remain these. Yeah, is there anyone more with this out here?
Sorry, I didn't get, what do you exactly mean?
Fine. Why are they connected? This is what I mean.
But it's finite unions of intervals? No.
Yes, it's unions of unions, but yeah, sure. It will end up being a union. And that has to be semilinear. One can compute. Not me, but one. Let me define my modular free formula. This is that union of intervals. So in short, yes, but you'll get a collection of these sets.
Maybe you can read it a little.
Yeah, sure, fine. So if you give a semilinear set
Yeah.
with p parameters, one can compute a value b and then look at the modulo classes in the p-dimensional space with respect to b. This set S for a given modulo vector v is just all the values b where you're on that modulo. And you can take this set and they're all, so all of these S are effectively definable by a union. That's the short of it. There are a few more statements that keep complexity. So you stay in AC1 when you're doing this, but I don't have to throw. Is that okay?
You have a reduction to a union of a modulo free predicates. You can say.
Yes.
So the lemma is not finished, right? I mean, I understand that the lemma is true for every big B, but then you said you can compute a big B to achieve even something else, something more than this.
Yeah, one can compute big B in AC1.
No, but I mean that set there, S in square brackets,
Yeah.
is always effectively definable for every big B.
Oh, yeah, you're right. Sorry.
That's
Yeah. I'm being
something else. That's not really.
Yeah, penalty observed. Yes, sorry. Thank you.
So, okay,
Sorry.
we can put a big B such that you achieve equipositive density
Yes.
and computable modulo free similar set.
Any more for anyone? Cool. Now, I will assume a modulo 3. I will assume my definition is acyclic. Now a couple more definitions. I want to skip for the sake of time, but I don't know if I
You
can.
don't need to do it in AC1 or anything, right? Because this is just to present the dichotomy, because S is fixed, it doesn't enter in the picture.
That's true.
You can compute it, doesn't even need to be computable actually, this is for correctness what you want. It's not that it exists.
Fine. I'm just choosing what to present next. So, yeah, I want to write down a nice statement. I want to keep examples. I'll get rid of this. Or definitions. So something I'll call compounded isolation. Let S be semilinear. Well, I'm just going to make the assumption now that this is semilinear modulo 3. So I'm not going to bother saying I'm writing that every time. It's got a bounded isolation if there exists some value L that's at least 1, such that for all delta is 1, there is a satisfaction of parameters and a particular value within the set such that firstly Yeah, I should have made some notation of this, but I haven't. I'll call this S T, just to save time. So if, firstly, if this set around this constant size interval of width L is not empty. So if there's a point in an interval small or that contains a point in this set, and on both sides of the interval either side, for like width delta, I do not have any points. So this is S T intercept x minus delta to x minus 1. That's empty. So in a sense, I'm isolated on the left, and I'm isolated on the right. It's like x delta. So pictorially, this looks like I have that was a bad choice, but for x and x plus L minus 1, there are some points that are in ST. Then there's a large region over here all the way out to x minus delta where I'm empty. And there's a really large region over here to x L plus delta, which I'm empty. So in a sense, for whatever delta you like, there is a point in the set such that after a small little neighborhood of width L, I then have so-called unbounded isolation, this huge seed of points. And the reason I define this is that it's not too hard to see, though I won't show it, that if S has unbounded isolation, then the reachability problem set this is hard. In a similar kind of way to how we just have signal. So you can imagine this, roughly speaking, being your signal on plate set with that stuff. Very roughly speaking. And then, yeah, I don't think I need to go any further. The reason I got this part, heat flows
Is that negative or interval? It's not in this class.
which one, sorry?
Which is negative for interval.
Yes.
It is there or
It's not there,
it's not?
which is good. Because I know.
All right. So
I think it's easy. And now I will define.
That's kind of exactly saying that this d of A is 0, right?
Exactly. Yeah. Arguing that
In
if you
this
have.
case, it's d of A is
Yes, exactly. I'm going to give one more definition and then that will come up. We have an equivalent, following our equivalent, so we can jump between being dense, not being not having unbounded isolation, and being a finite union of the following object, which are kind of four simple sets that we'll work with. So definition.
So not is literally the same as this 0.
I don't have time.
It is the same.
It's the same, yeah. So if you have density 0, then you will have unbounded isolation. And if you have unbounded isolation, it's pretty easy to see at density 0, because if you take a point in this area, and then grow an interval either side, the density will be like 1/2 delta, something like that. Or rather, at most L over 2 delta, and delta can grow. So on all these row chains, this is going to be technical. I'll then try and give you a picture, but it's not super important. These examples, or the last example, will capture most of this.
Here you already assume you don't have modulo. It's somehow There's no model weight here.
It's all wrong, yeah. Yes, it's really just looking at the intervals. Yeah, you can't like jump through.
Because, for example,
X
the
now.
case 4, it actually, by itself, it has bandwidth isolation.
Yes. That's the whole, yeah, that's why I first proved this. So that's. Well, we wrote this while the rational. So rational constant. And we'll say a sequence of intervals. Exactly m plus 1 is a row chain if one of them is one-sided infinite. So minus infinity is 0, for example, and they're all disjoint. Analyze disjoints.
These are subsets of the integer.
Yeah. They're intervals. If they're disjoint, if their size is increasing with their index, then the stones are as well. They are in sequence relatively close together. This is why we call them a row chain. So this is for all indices. The distance, I'll define distance in a minute, it's exactly what you would think it would be, between a pair of not necessarily consecutive intervals, but a pair of consecutive sized intervals is bounded above by this constant times the size of the smaller interval. So the distance between two intervals is the minimal distance between 2 points there. So the distance between these 2 points is t, or these 2 intervals is t. And the final condition, which is a bit weird, that I will remove as another word, if this example doesn't observe it, it's too small of an example. So for all indices, you have an interval, all small intervals will either be on your left or on your right. So either for all smaller intervals, that's j with a smaller index, the intervals are on the right. So I'm using this notation to say the whole interval is like on the left of a given interval, or all smaller intervals are on the left. So
Could you read loudly for the last point?
yeah, I'll draw an example and then I'll read it loudly because it'll be nice to point at something.
And so, just a general question. So, big picture is like that. You are massaging, you are proving your main theorem. Kind of, you are trying to massage the situation so that small density thing will actually come close to the reachability.
Pretty much.
But the big density things will come close to being what?
They will break down into these core objects. I'm just about to write down the proposition.
Which will be kind of like coverability or like everything.
They're bigger than coverability somehow. They look like 6. That's why I showed 6.
Okay.
So it's not quite coverability. Yeah, it's not. It's really not like quite that coverability at all, actually. And the algorithm for showing these are in AC1 is also fairly different to coverability. Okay, I'll draw a picture as promised. Right, let's do the right side. So imagine I have an interval, which is an infinite, n is going to be 3. Yeah,
The action for, I think I'm probably missing something. It doesn't say the same thing that the intervals are ordered from left to right.
not quite.
Can you please read this before?
Yeah, I'm just about to read the example, because I think it helps seeing a picture. So, yeah, looking at
At the end of A3, there is something dot size of AI. What
That's
is
a row, that's-
something, row.
Parameter of the definition.
So condition A4 says for every interval, so look at I4, for example, all intervals that are smaller, so for all J with indices 1 through 3, so smaller intervals, they're either all on the left or all on the right. So this notation says I4 is on the right.
Also, the or between
Yeah.
I and I.
Ah, sorry. You're right. Thank you. Yeah. Very important. So.
And it would be even worse.
Yeah. So I4 is obviously on the left of everything else, because one side of it. Then I3, look all things smaller, they're all on the right. Now look at I2, all things smaller on the left. It's not that they're necessarily in an order. You can violate this if I give you a very similar looking example. I should put I1 here, then I3, then I2. If you look at I3, all the intervals are smaller than, well, they're on both the left and the right. So this fails A4.
So intuitively, if you go from smaller to larger,
Yeah.
you start in the center and you add the new one, either extreme to the left or extreme to the right.
You can view it like that as well. Yeah, that's absolutely fine. And A3 says that the distance as I go between larger and larger intervals has to remain within a constant size of the size of the interval. So in this picture, it says that this distance is something like the constant, maybe by my crappy drawing, something like rho equals 2, right? Like this gap is roughly twice the size of my other, maybe rho is 3. And it also says that this gap, so the distance between I2 and I3 is something like a constant times the size of I2. Now I'll give this. Any more questions about that definition? First observe 6 is an example of this, right? There's not enough intervals to make condition 4 interesting. But condition 3 is satisfied because the distance between what will be I1 and this will be I2 is exactly 1 times the size of that interval. So proposition, why have I shown you this proposition? The following are equivalents. 1, S, well, the density of S is positive. 2, S does not have unbounded isolation. And 3, S is a finite union. Of merchants. But if we're little asterisks here, this is not strictly true. You have to do a little bit of massage on it, but more or less this is
I
true.
mean, forever T.
That's what I'm hiding at. Yeah. Yes, it's the right answer. In fact, it's instead of a row chain, it's something we call a building block.
This is can be under the assumption of eliminating.
Yeah.
Avoiding.
That's what.
What are you using?
I'm basically lying to you in 3 a little bit, but I really don't want to tell the truth because it would be the whole domain of the seminar. There's a definition that builds on row chain that covers this for all T. Because it could be for a particular S, you can have 2 intervals that swap sides, right, or swap even in size. I can have them grow differently depending on the instantiation of T. And then it's kind of like not clear whether S is a finite union of just one or multiple of these chains. So I need to do some more work.
All these propositions are under the assumption that S is modulo 3.
Yes. And well, yeah. Yeah, it's I won't prove it. To show, I'll give you one line for each. For one implies two, Wojtek's already sort of kind of talked about it a little bit. It's actually easy to see it in the other direction, which is that if you are isolation, if you have unbounded isolation, then there is a point with arbitrary delta either side where you hit nothing, so your density is like L over 2 deltas, that's tiny, and so density is 0. 2 implies 3, really hard, not going to talk about that. We use well-quality order. The finite union we get is laughably large. You have to do a lot of analysis on the ratios between all intervals and all gaps. I'm happy to talk about it, but not now. And the last is 3 implies 1. That's not particularly hard to see. That's kind of what A3 is doing a lot heavy lifting for. The density here is going to be something like 1 over 2 rho, approximately speaking. If you look at a point here and you grow an interval around it, you're promised that after the interval grows to size 2 rho, you'll start eating into the next interval. And as you're eating into this interval, as this grows, then after a while, you'll then start eating into this interval. So you're kind of chained between growing and growing intervals. Your density will end up being something like 1 over 2 rho, 1 over 2 rho equals 1. And so then, if you are a finite union, density, if you have positive density for 2 sets, your union of the union will have positive density. So this is all fine under the closure properties that are relative results. Okay.
What's isn't the third line with the kind of false statement that finite for chains equivalent to being a union of a half line and finite union of intervals?
A finite union of half lines.
So a half line and a finite union of
no, the size of the interval matters. Because I can give you this set. That's an interval. Yeah. Got size 1. Reachability here. Well, I've got nothing here. Reachability is half to this set.
Oh my God,
this.
But just 1 point? What is this?
Just
T.
The density here is 0. If I look here, and I look at the interval around here.
But this interval contains 1 point inside, and at most 2 T points outside, right?
Yeah.
So it's
This density is 0 because T can be
Whatever you like. It's a parameter. If I just had a constant point, like 0 or 10, yes, you're fine. That kind of comes back to the y as a semi-linear set factorized.
You would also have condition 3 then.
Yeah, condition 3 fails, yeah.
But if T would become fixed, then it wouldn't.
Exactly. Yeah, you'll just pick the capital size.
Yeah, these are some of them.
Cool. Yeah, that's why I showed examples, right? It's helping us through. I was so optimistic about what I would be able to present. I'm 4/7 of the way, but I'm more than 4/7 of the time. So I'm going to have to skip something. I might have to skip a cool proof. I really wanted to show some, because this has been quite definition heavy. I wanted to show some technical proof details because some of them are quite nice, but I might have to skip it. But I want to at least give you a feeling as to why it's happening. So another proposition. If X is a row chain, okay, let's say if you're given a semi-linear set that's not characterized, then reachability into the semi-linear set is in it. And I want to talk about this as much as I can, but only from the lens of example 6. So we're not going to have this in full generality, but the way we do this harks back to some of the stuff we talked about for this interval stuff at some point, which is why I want to talk about this. And if you get that for any road chain, your reachability problem is an AC1, then you're done, right? Because you can turn, if you've got positive density, you can turn into a finite union, and then you're good to go, right? This finite union is finite, so we stay in AC1 if we just put if we put reachability to one road chain in AC1. Okay, so I will choose board. I will kill manual isolation. So I'm going to turn. So yeah, we're going to, for the remainder of the talk, consider we're going to fix this now. I should use A, but I've used S. So step one, I'm going to transform the problem somehow into some problem of matrix multiplication. So I'm given an acyclic automaton. Let's just give a dummy example. So A, B, C are integers. And I will turn this into a matrix with polynomials representing the updates. We'll call this an A. That's what I've got on the notes. This polynomial says I can just stay still. So if I look at A squared, and I look in particular at what I can do from node 1 to node 3, this will be equal to, well, x to the 0 times x to the c plus x to the a times b plus x to the c times x to the 0. And if I'm using a matrix that belongs to the matrices where I have Boolean semi-ring, then this will work out to be x to the c plus x to the a plus b plus x to the c. This is going to be a plus b plus x to the c. So here, 1 plus 1 is 1, 1 times 1 is 1. Yeah, it's just Boolean coefficients. Any questions? Cool. That's the second.
Regular paths, right?
Second, sorry. Yeah.
Kind of regular paths.
I'm reading over parts, yeah. And this allows me to stay at a state. So this path, so to say, is I stayed at 1 for 1 step, and then I went to state 3. This says I went to 2 and then to 3. And this says I went from 1 to 3 and then I stayed at 3 for a step. So more generally, A to the n I j will be the polynomial of paths, let's call them pi, from I to j of length at most n. That's what. So it's not exactly equal to n because I can just sort of hover in a state if I wanted to. Of the polynomial with degree and weight of the path. This should create alarm bells. Should bring alarm bells, sorry. I'm now going to go. So it should bring alarm bells because you may now want to have a polynomial with exponentially many terms. So computing ATM might be right. What am I going to write down? The example for which under ATN IJ contains exponentially many terms. It's rather simple. I will draw it in just a moment. So if I have this machine, And let's say I call this state 1 and I call this state n, then right, this is the best version of examples. To kind of clarify. Obviously, in this case, you can reach any number you want, so reachability is not hard, but you have to know that in advance, right? Wow, with my for coverability, you'd use the max plus semi-range. You just take the greatest value and just kill all other terms. So you could impose the equation. And then for coverability, this is fine. You then have one term in every cell in your matrix, and then you can do repeated squaring. This is how you get efficient algorithms. If you can do A times A in AC0, AC0, then you can do A squared log many times to get A to the n in this one. That's the very long short of why coverability is in AC1. We're going to do the same thing, but we're gonna have to choose a different equation. It's not clear if you choose the largest value that you're gonna reach your target set. If you think quite literally about the example where it's there and what is it? Yeah, S is between minus infinity and 0 or t and 2t. If you always take the greatest value, then you might only store a value in your matrix that's greater than 2t, but you could have been able to reach like t to 2t. Similarly, if you take min instead of max, then you might only find a point between 0 and t rather than a point between t and 2t. So it's not clear what equation we should use.
So a question about, so matrix product is in AC0, because you have to fix the dimension of these matrices. I mean, what I remember in general, matrix product is in L, but here you're going lower, and I wonder, what is the parameter that allows you to do that?
That's a good question. How comes that afterwards?
But the dimension of this matrix is not fixed.
No, it's number of states.
Right.
Okay. You say that in general matrix.
Yeah, general motion expression is
And C, sorry, in C. I meant in C1.
It's the site.
It's one, and then for linear algebra things in C2.
I'm
So we're lower. So I wonder, there must be something for this solution.
yes, there's one. It obviously is. I don't know right now. I'd have to sit down. So we want to keep the same structure. But we can't store all the polynomial. We can't use this equation. I'm going to show you the equation to use instead. This is where it's getting real optimistic. So I will kill really what the examples. I'll kill subsets. I will talk through them in a moment. So equation 1 says, if I have terms xi, xj, and xk, then instead I don't need to store 3 terms, I'm going to store 2, which look like x, ij. I will explain what that is in a second. And why this makes any sense in a minute after the planet. So this term is just all the terms we imagine. That's correct. Yeah. So I'll just draw the example. I claim that this equation is reachability preserving to this target set. So if I mark on I, and then I mark on some j, so j needs to be within k. I mean t, it should be t, so. I mark on j that is within t of I. So for example, I can mark j as here, and then I have a k that I mark within t. Then I claim that I, j, k intersect with the target set if and only if the interval between I and j and then the singleton k intersects. I mean, in this case, it's clear because the interval between I and j intersects here, but we already have j and k within such interval, so that's fine. I could have instead had this, and the interval ij doesn't exist.
Sorry, could you
Yeah.
say once again, what are you proving?
I'm
I didn't,
I'm
never
justifying
understand,
that
this first line, what
Yeah.
does that mean?
I'm how do I explain this? So yeah. Recoverability, you need not store all the terms xi, xj, whatever, you just store the max. Here I'm coming up with a new system of equations. Instead of storing max, I'm going to store some alternative terms. In this case, I'm going to store the interval of terms xi through xj. So I'm introducing new terms and I'm simplifying the reachability set. So instead of it being some sort of random terms, like exponentially many of them, I'm going to have some large interval of terms, maybe some simple. So I'm coming up with some new equations to store fewer terms, and that the new polynomial will intersect with the target set if and only if the original one.
So you keep some kind of, instead of ijk, compressed version, which you claim is somehow equivalent.
Yes. Yeah, exactly. Compressed version is the reason why I'm saying this. In a sense, I'm only storing the kind of most important terms.
So 3 lines is kind of equivalent in this.
Yes.
And kind of equivalent means one side intersects the target set and only the other side does.
Yeah. Might not be at the same point necessarily, but for just saying yes or no to reachability, that's all.
It's like you saturate your system, your VASS, you add a burden. And it's add up in pass and transition.
Sorry, what do you mean? Misunderstood.
It's like you add up all between I and j. So
Yeah. Yeah, in a sense, I'm saturated. Say, all of these points in here, I don't know which ones are reachable, but they may as well all be reachable. If you remember from subset sum earlier, the original example, all of the xi's are small enough. So in a sense, with respect to the width of the interval t2, t, it didn't really matter. I could kind of reach it. Kind of morally, this is like the feeling. I don't really know if I can reach I plus 2. It doesn't really matter because all these points are kind of small relative to the target set. Does that make sense? That's one equation. The other equation, and this was to justify, yeah, I should probably words on top of this again. This was to justify why this equation works. So if I pick an I and a j that are within t of each other, for example, if I had I here and j here, then the interval between I and j intersects the target set if and only if I and j don't. And that's fine because if I and j were both outside the target set, then the interval won't intersect as well. So this equation is pretty straightforward. Preserving reachability, whatever preserving reachability really means, is fairly clear cut. There's another equation which is not
What if I is on the left of the interval and
I
j
is
is
on
on the right?
so you're saying I is where? Here?
I is here, j is on the right.
This is not valid. So they have to be relatively close for me to be able to compress. Like in the subset sum, the items have to have small values. Or here the reachable points have to be close enough together. Okay. Second equation, it's very similar, slightly more complicated. I'll write this down right now while I write this down. New equation, I'm going to compress the same, or rather like interval over I and j, but now I might have another term h that's supporting me on the left of this. So let's see what this looks like. So imagine now I can do what is that work about? I could place I here, I could place j here, because j minus I is just any natural number, that's fine. But I must have an h that is to the left of I by at least k. That would then place h in here. And so then if I take the interval between I and j and the value h, I'll intercept the target set if and only if IJH intercept the target set. Does that make sense? It's not as obvious at this point. It's the same thing, just a second equation. Maybe you just have to take it on face value.
For me, it's unclear what's the big picture. Where are you headed?
Yes, yeah, I'm just trying to write down. Yeah, I had to kind of introduce the equation before I can write down the next statement. Which is suppose you have a arbitrary polynomial with as many terms as you wish. So the example I just rubbed out with maybe exponentially many terms. Then there exists at most two of these kind of special interval terms. Right, think this is the thing. So there's at most two terms of this form, such that let's say P1, P2, such that they're equivalent. I'll explain what that seconds. This just says there is a term in P such that X is in the set if and only if there exists Y such that X and Y in P1 or P2 such that Y. So in a sense, their reachability was some way. And I claim that the amount of polynomial you gave me, there are at most two of these interval terms that capture reachability. In the case of recoverability, you'd only need one term, the singleton term that is the greatest. Here, I don't promise that. I promise that there are 4 values, and you need to store the 2 intervals. And this will be what you need. In general, when S is not this exact set, this number changes, and it will depend only on rho, the distance between them, and n, the number of intervals. Precisely, it's rho times n plus 2n. So some large value. There's a constant number of terms. So you get some like large collection summed together of these interval polynomial terms. And then we do the same thing. I rubbed it off here. We can take the matrix A. In AC0, we can find the small number of interval terms that preserve reachability with respect to the original polynomial, reduce it down, and then we can square that matrix in AC1 and repeat this process over and over again to get an AC1 algorithm. The very end, you'll have a matrix ATN, then you just check whether this polynomial, which will be a collection of sum of most constantly many interval terms, you just check whether there exists a term x the x in here where x is in your target set, and that's easy to do. That's the high level idea. I don't have time to go into anything else. The seminar ends in 2 minutes as far as I'm aware. We have analog definitions. I think I got off the main theorem here. We have analog definitions for the other dichotomies. So if I give you natural semantics, so all the updates are in the natural numbers and all the configurations are in the natural numbers, then we have a modified definition of density and a very similar approach. And then for VASS, we have a different definition, which we call uniformly quasi-upward closed. And if we uniformly quasi-upward closed, then reachability is easy, otherwise reachability is hard. Happy to talk over cake. I think I should wrap up there. Thank you. Any questions?